Hi, my name is Dr.AhMath. Welcome to the course of Biophysics 1. In this lecture, we are going to discuss the solutions for the quiz on Bernoulli's equation. The Bernoulli's equation is the conservation law of energy for the fluids. It basically tells us that if you have a pipe with the fluid which is passing through inside this pipe, and if you decide to cut this pipe at some point here, the total energy of the fluid there is going to be the same as if you would cut this in any other place of this pipe. And we are going to find out the total energy of the fluid by adding the pressure P plus the potential energy rho g y plus the kinetic energy 1 over 2 rho v in the square. So we are going to solve a couple of problems using this equation. So a liquid with the density 1.65 grams per second cube flows through a horizontal pipe with a varying cross sections. So in the first section, the cross-sectional area is equal to the 10 centimeters in the square, and the flowing speed is 275 centimeters per second. The pressure is 120 kilopascal. In the second narrower section, the cross-sectional area is equal to the 2.5 centimeters in the square. So we need to calculate the flow of the narrower section. So basically, we can use so we should use actually the continued equation in order to find the velocity, the speed of the fluid at the another section. So you've got the pipe with the two different cross-sectional areas. So the cross-sectional area here is equal to the 10 centimeters in the square, and the cross-sectional area here is going to be equal to the 2.5 centimeters in the square, right? So the velocity here is going to be equal to the 275 centimeters per second. And what's going to be the velocity here? So since the cross-sectional area is decreased 4 times, then the velocity is going to be increased 4 times, right? So we discussed this before. So since the multiplication of the cross-sectional area to the velocity should be always the same, so if you decrease the cross-sectional area, the velocity is going to be increased for the same amount of times. If you don't agree with me, we can just solve this. So we know that A1 times V1 is going to be equal to the A2 times V2. So from here, we can find that the V2 is equal to the A1 times V1 divided to the A2. So it's going to be equal to, so let me write down the A1. It's going to be 10 centimeters in the square. So let me do not write down the numerical value for the velocity 1. Divided to the second cross-sectional area is 2.5 meters in the square, right? Or centimeters in the square. So if you divide the 10 to the 2.5, it's going to be 4 times V1. You see, so the second velocity is going to be 4 times bigger than the first velocity. So that is why the velocity at the more narrower place is going to be 275 times 4. It's going to be 1,100. So basically, velocity t is equal to the 1,100. Okay, so let's go to the problem number 2. So it's I think very similar to the previous one. A liquid flows through a horizontal pipe with a varying cross sections. In the first section, the cross-section area is 10, flow speed is 275, and the pressure is 120 kilopascals. In the second, more narrower section, the cross-section area is 2.5 centimeters. Calculate the pressure of the flow in more narrower section. So again, we need to write down the total energy. So the total energy, or we need to use the Bernoulli's equation basically. So I've got the horizontal pipe with the two different cross-sectional areas. So I've got the cross-section here and here, right? So horizontal, it means that the height of the velocity here and the height of the height of the fluid here and here are the same. So let me write down the Bernoulli's equation. It basically is equal to the pressure plus the rho g h1 or y1 plus 1 over 2 rho v1 in the square is equal to the p2 plus rho g y2 plus 1 over 2 rho v2 in the square. So since their heights in both of the places are the same, it means that y1 is equal to the y2 and we can just simply cancel them. So numerically, they are the same values. For example, they might be 2 there, 2 there. You can just put them, if you put one of the terms to the another side, right? So 1/2's are going to, sorry, so I'm not going to cancel 1/2's. So what we have to do is we need to find the P2, right? So we are given everything else. So the P2 is going to be equal to the P1 plus 1/2 rho V1 in the square. So this term is going to go to the left. It's going to be minus 1/2 rho V2 in the square, right? So it's going to be equal to, P1 is equal to the 120 times 10 in the power of 3 pascals, right? Kilopascals, 10 in the power of 3 pascal. So this is the 3. Plus 1/2 rho, it's going to be equal to, so I'm going to write this in a moment, times V1 in the square minus V2 in the square. Good. So I need to calculate this. So what I'm going to do is I'm going to write this 120. Oh, let me calculate this. V1 is equal to, the velocity in the first section is 275 times 10 in the power of minus 2 meters, right? It's meters per second. So it's 275 centimeters per second. It's 10 in the power of minus 2 meters per second. It's going to be 2.75 times meter in a second, and the velocity in a second, molar over cross-sectional area, is going to be 1,100 or 11 meters per second. So basically 4 times bigger than in the previous one. So I just need to do this. So 2.75 in the square minus 11 in the square. It's going to be equal to minus 1. So I'm going to write this 120 times 10 in the power of 3 pascals plus 1/2 times the rho. I'm going to write down the rho in a moment. It's going to be minus 113.43. If you just plug V1 to here and V2 to here, you're going to have minus 113. So now we need to write down the rho is equal to rho is equal to the 1.65 grams per centimeter cube. So rho is equal to the 1.65 grams per centimeter cube, right? What we have to do is actually, we need to write this in terms of the kilograms per meter cube, right? So in order to be able to add the pascals to the pascals, so it's going to be 1.65 times. So if you remember the gram, 1 gram is 10 in the power of minus 3 kilogram, right? And 1 centimeters is 10 in the power of minus 2 meters, and this should be in the cube, right? So it's going to be 1.65 times 10 in the power of minus 3 divided to 10 in the power of minus 6 times kilogram divided to the meter cube. So 10 in the power of minus 3 over 10 in the power of minus 6 is going to be 10 in the power of plus 3. And it's going to be 1,650 kilogram per meter cube. So I'm going to here put 1,650. Okay, so we need to always try to put the proper notations. So now I'm going to just do the calculations. So minus 113 times 1,650 over 2. So it's going to be plus 120,000. I think we are doing something wrong. So let me use just a calculator. 113 times 1,650 . It's going to be 93,000 minus 93,000. So it's going to be 120 times 10 in the power of 3 pascals minus 93.22 times 10 in the power of 3 pascals. So if you subtract them, it's going to be minus 120. It's going to be 26,000. So it's going to be equal to the 26.77 pascals. Good. So the pressure is decreased, right? And we can understand this from this equation. So if the velocity is increased, then the pressure is going to be decreased. So the pressure P1 here was equal to 120 kilopascals, and here it's only 26.77 kilopascals because it's the velocity is increased. Okay, good. So let's go to the problem number 3. So water moves through a pipe in a steady ideal flow. At the upper point, the pressure is equal to the 120 kilopascals. The flow speed is equal to the height, and the diameter of the pipe is equal to the 1.5 centimeters. At the lower point, located 5 meters lower, the pipe's diameter is equal to the 3 centimeters. What is the pressure at the lower point? So we need to use the Bernoulli's equation, but everything is, so we need to try to use this in a more clever way. So you've got a pipe and the 2 different section areas, the heights are different as well. So I'm going to just make it, let's say this height here is going to be y1, and this is going to be equal to the 0. Okay, so the second one is here y2, and let's say this is equal to the 5 meters because it is given that the second point is 5 meters lower, right? So it's also given that on the upper side, the pipe's diameter is equal to the 1.5 centimeters, right? So I'm going to write down this. So if you remember, the volumetric flow rate using the continuity equation is equal to the A times velocity, velocity, right? So while this A is equal to pi times the diameter in the over 2 in the square times the velocity. So if you take out 1/2 out of the brackets, you can write this as a pi over 4 times the diameter in the square times the velocity, and this is the volumetric flow rate, and this is always the same no matter what is the cross-sectional area of the pipe, right? So it means that if I increase cross-sectional area from 1.5 to the 3, it means twice, right? I have to just multiply the diameter to the 2. So I'm going to just substitute this in this way. It's going to be pi over 4 times, instead of d, I'm going to write 2d, right, in the square, and this is multiplied to the velocity. So I would like to know how the velocity is going to change. So it's going to be pi over 4 times 4 times d in the square, right, times the velocity. So if I would like to have, again, the original quantity as in the beginning, what I have to do with this v, right? How I need to change this. So the answer is obvious. I need to multiply this as a 1 over 4. So in this case, this 1 over 4 is going to cancel this 4, and I'm going to have, again, the original quantity. It means that if the diameter of the pipe is increasing twice, then the velocity is decreasing 4 times, right? So the velocity is going to be decreased 4 times. So you can do these calculations using the continuity equation as well, but I'm just going to use this logic. So the velocity at this point, at a higher point, let's say, v2 is equal to the height, 0.8 meter per second. Then the velocity here at this point is going to be equal to the 0.02 meters per second, because the velocity changes only when I change the cross-sectional area of the pipe. So if I decrease this, then the velocity is going to be increased. So, and also we are given that the pressure here at the higher point is equal to the 120 kilopascals, and what is going to be the pressure P1 here. So the only thing which I need to do is I need to put everything which is given into the Bernoulli's equation. So Bernoulli's equation is equal to the P1 plus rho G y1 plus 1 over 2 rho v1 in the square is equal to the P2 plus rho g y2 plus 1 over 2 rho v2 in the square, right? So the first thing which I'm going to cancel is this one, because I'm taking the y1 to be equal to the 0. The rest I'm just going to put the things down. So I'm going to P1, it's going to be P2, So let me put with the values, right? So the P2 is going to be equal to the 120 times 10 in the power of 3 pascals, right? So plus, so the rho, the density of the fluid is going to be, it's water, so that it means that the density is equal to the 1000. So the rho, the density of the water, is equal to the 10 in the power of 3. G is 9.8, and I can take it as a 10 in order to make our calculations more simple. YT is going to be equal to the 5 meters, right? So we take the height at the second point as 5 meters, plus 1 over T times rho, again, is 10 in the power of 3, and the velocity, in the second part, okay, so I still need to put this point to here, right? Okay, so the velocity in the second one, it's going to be 808 in the square. So 808 in the square minus, so if this term going to the right, it's going to be 1 over 2, again, 10 in the power of 3 times 202 in the square. So we just need to do our calculations. It's going to be 120 times 10 to the power of 3 pascals, plus, so 5 times 10, it's going to be 50. So 50 in the cube, sorry. So 50 times 10 in a cube pascals, plus, so I need to do this two calculations. I'm going to use the calculator in order to do this. It's going to be, so 0.8 in the square minus 0.02 in the square, and all of this thing over 2. It's going to be 30,000. 30,000, 10 in the power of 3. So if I just add this 80 and 30, it's going to be 80, right? And 80 plus 120, it's going to be 200, 10 in the power of 3 pascals, or 200 kilopascals, right? So basically the P1 is greater, right? And it's, okay, good. Yeah, so we've calculated this using the Bernoulli's equation again. Okay, let's go to the next problem. A fluid of density rho is given as 1,350 kilograms per meter in a cube. Flows in a horizontal tube with the variable cross sections. And the first segment, the cross-sectional area is 8 centimeters in a square. The flow speed is 300. In the narrower segment, the cross-sectional area is 4. The pressure is 66 kilopascal. What is the pressure in the larger cross-section segment, right? Okay, so again, we need to use the Bernoulli's equation. So it's going to be P1 plus rho G Y1 plus 1 over 2 rho V1 in the square is equal to the P2 plus rho G Y2 plus 1 over 2 rho V2 in the square. Again, the tube is horizontal. It means that the height in the two parts of the cross-section cross-sections are going to be the same. So the V1, so Y1 is equal to the Y2. I can just cancel them. So in the cross-sectional area, where the cross-section is equal to the 8 centimeters in a square, the velocity is equal to the 300 centimeters. So if the cross-section area is decreased, what's going to happen with the velocity? If I just make the pipe a little bit more narrow, it means that the velocity is going to increase, right? And when we're talking about the connection between the cross-section and the velocity, we know that they are proportional. Basically, it means, so they're inversely proportional, but linearly. It means that if the cross-section area is decreasing for 2 times, then the velocity is going to increase only 2 times, not 4. So it's going to be centimeters per second. 600 centimeters per second, or 6 meters per second. Then I can just like put everything together to here in order to find the pressure in the larger cross section, right? So let's assume that it's going to be velocity 1, it's velocity 2. So we know the pressure in the narrower section. So that we know the P2 is going to be 66 kilopascals. So we need to find a P1. So I'm going to find a P1. It's going to be P2 plus 1 over 2 rho V2 in the square minus V1 in the square. And I obtain this term if you take this term and put this to the right and just take out 1 over 2 rho from the brackets. So it's going to be equal to, pressure in the second point is going to be 66 times 10 in the power of 3 pascals plus 1 over 2 times 1,350, or you can just write it as 1.35 times 10 in the power of 3 kilogram per meter in the square. And then I'm going to just put here V2 is 6 meters per second in the square minus V1 is 3 meters per second in the square. So it's going to be 36 in the square minus 3 in the square. It's going to be 27, right? So I'm going to calculate this. 36 minus 3 in the square divided to the 2 times 1.35. It's going to be equal to the 18. So it's going to be 66 times 10 in the power of 3 pascals plus 18.22 times 10 in the power of 3 pascals. And if I add this to the 66, it's going to be equal to the 84. 84.22 kilopascals.